All right, this is the solution for the Chapter 1 quiz for Physics 102. Which of these is not a valid charge? All right, this was based on the idea that all charges are integer values of the fundamental unit of charge, 1e, which is 1.6 times 10 to the minus 19 coulombs. All right, so that means that you can have, one electron, or you can have two electrons, but you can't have 1.5 electrons, for example, or you can't have 1.5 protons. So we're looking for a quantity here that is a multiple of this 1.6 times 10 to the minus 19. Now, this is 2 electrons. This is 1 proton. This is a whole bunch of protons. So if I say 54 coulombs divided by 1.6 times 10 to the minus 19, let's see, I get 3.375 times 10 to the 20th, or I can write an integer value with 17 zeros, all right, however many zeros that is. So that's a whole bunch of protons, whereas this one is 5.4 times 10 to the minus 19 divided by 1.6. It's like what? 3 point something. Oh yeah, 3.375, 3.4 protons. And so obviously you can't have a fraction of protons, so that's not the right answer. So B, or rather that's not a valid charge, so that is the right answer. In this figure, a ball is made of a conducting material. And that's the key, that it's a conducting material. What is the charge of the ball? You can have two scenarios. One, you can have a material that is negatively charged so that it looks like that. Or you can have a ball that is neutrally charged so that you get an induced charge on the ball and it looks like that. So it can either be negative or neutral in either case. Now, if it were an insulating material, it would have to be negative. So if this was insulating, if it were an insulated ball, like a wooden ball or something, in order to have the same scenario, this would be an insulated ball, an insulator, like wood or plastic or whatever. The whole thing would have to be negatively charged because you don't get that type of induced charge on an insulator except in some small scale places like with the balloon picking up the paper. We got some induction we got the cells, molecules, were polarized, but that's on a much smaller scale. So, all right, let's keep on. What is the charge of Q1 if Q3 is negative? All right, so if Q3 is negative, that means Q2 has to be positive. And here, if Q2 is positive, that means that Q1 is also positive. So the answer is A. Consider this configuration of charges. Which vector best represents the net force acting on the rightmost charge? All right, so due to this charge, I have a force that is in this direction. And due to this charge right here, I have a force that is bigger in that direction. That means that the net force is going to be E. What is the magnitude of the force on the 6 nanocoulomb charge in this figure? All right, first of all, I want to figure out what is this distance. So I have a triangle, 0.5, 0.5, so I say the square root of 0.5 squared plus 0.5 squared. And that's equal to 0.71 meters. And then I want to find the force, K, QQ over R squared. Q is 3 nanocoulombs and 6 nanocoulombs. Notice I'm converting those to coulombs, 10 to the minus 9, divided by that 0.71 squared. So that cancels with that. And I get 3.2 times 10 to the minus 7. That's newtons, so that answer is A. And then I also want to know what is the direction of the force on the -6 nanocoulomb charge. So the force is actually in this direction. And I know since this is an equilateral triangle that this angle is 45 degrees. But notice that is 45 degrees above the negative x-axis. So let's go and look at our answers. It's not above the positive x-axis, so that can't be right. And it's also not below the positive x-axis, so that can't be right. 30 degrees, that just doesn't make any sense. And so let's look at this. This has to be the right answer. Let's go see. That's 135 degrees. So that's saying that this angle is 135 degrees. Well, I know this angle is 90, and this angle is 45. So indeed, that is 135 degrees from the positive x-axis. So that is the correct answer. Protons accelerate from rest in this electric field. What is the velocity of the proton after 2 seconds? All right, several things we have to do here. First, we have to find the force, which is QE. This is a proton, so it's 1.6 times 10 to the minus 19 coulombs times 100 newtons per coulomb. Notice I said this in the screencast, but volts per meter and newtons per coulomb, those are the same units for electric field. So that is 1.6 times 10 to the minus 17 newtons. And then I know that F equals ma. So A then is equal to F over m. It's 1.6 times 10 to the minus 17 divided by the mass of a proton, which is what, 1.67. Gosh, I get 9.6 times 10 to the 9 meters per second squared. Really fast acceleration. And then I just want to know what is velocity. Well, I know that v is equal to v naught plus at. But v naught in this case is 0 because it's starting from rest. And so I just multiply this times the time, which was 2 seconds. And I get 1.9 times 10 to the 10. And that's faster than the speed of light, so that's not a realistic number, but I mean, these particles do go very fast, in fact. All right, let's look at this next one. I have two charges separated by a distance d. I have 2 points A and B, and I want to know where is the electric field the greatest in magnitude. So in this, you need to be able to draw the electric field vectors and draw them with relative lengths, like which one is bigger or not. So, for example, here, I have at point A, due to this charge, I have an electric field that is in this direction. And then, due to this charge, I have an electric field at point A that is half the magnitude of the other electric field and in the opposite, or excuse me, I'm sorry, that was a mistake, let me fix that. It's half the magnitude and in the same direction. So it's going to look like that. So those are my two electric field vectors, and so the net electric field will look like that. Now, over at point B, due to this charge, my electric field vector is going to look the same as it did at point A, except in the opposite direction, but same magnitude, because I'm the same distance from that charge, and it's the same charge. So now, where it comes important here is, due to this charge, my electric field over here is to the right, but it is, let's see, it's actually 3 times as far away from the charge, so it's going to be 1/9 the electric field that we had over here. All right, and that gives us a net electric field, which would be slightly shorter than this green line, something like that. And so the electric field is larger at point A. And just reiterate this. This electric field, notice that over here, this point, we're a distance d over 2. But over here, we're a distance 1, 2, 3 times d over 2. So we're 3 times as far away from the charge. And since the electric field is kq over r squared, since we're 3 times as far away, that means we have 1/9 the electric field. All right, this figure shows two charges in the electric field lines. The charge on the left has a magnitude of 6 microcoulombs, so 6 microcoulombs over here. What is the sign and magnitude of the right charge? Well, first of all, I know that field lines emanate out of positive and end in negative. So I know that left charge must be a negative 6 microcoulombs. And then I count the field lines. I have 6 field lines over here, and I have 12 field lines coming out of this charge. Since I have twice as many field lines, I know that my charge must be twice as big. So it's going to be plus 12 microcoulombs, which is B. All right, two charged balls are repelling from each other. What can you say about these charges? Okay, these two charges have to be either both positive or both negative. So they have to be the same charge. What can you conclude about these charges? And in this one, these are two separate situations. So let's just say that yellow is positive. And if yellow is positive, that means green is also positive. And if green is positive, that means purple is positive. So all three have to have the same charge. And you can make the same argument if they were all negative, you'll still find the same to be true. All right, metal ball hangs from the ceiling by an insulating thread. It's attracted to a positive charged rod. All right, this is exactly like we had before. Either the ball is negatively charged or it is neutrally charged. So it's either negative or neutral. Two neutral conductors are conducted. The wire is taken away and the charge rod is removed. Okay, so here, remember this is charged by induction, by the way. Not conduction, but induction because it didn't require any touch. When I bring this positively charged bar here, I get a negative charge here and a positive charge here. And then when I take away the wire, I keep negative and positive. And even when I take away that charged bar, I still keep negative and positive. So that would be C as the answer. What is the magnitude of the force F2? Well, Newton's third law says that for every force, then I have to have an equal and opposite force. So if I have 3 newtons here, I'm also going to have 3 newtons here. That arises from Newton's third law, but it also arises from Coulomb's law, which obeys Newton's third law. Notice that both forces are represented here. And so if I'm calculating the force for this charge or the force for that charge, I'm going to calculate the same value, okay? Because each of the forces is included when I'm calculating the force. Each of the charges, is included when I'm calculating the force. All right, if we increase one charge to 4Q, what is the magnitude of F1? So if I increase this charge to 4Q, then that's going to increase my force by a factor of 4. So if I increase this by 4, it increases my force by a factor of 4. Well, if it was 3 newtons, now it's going to be 12 newtons. That's C. The force between two charges separated by distance d is F. If they're pulled apart by thrice the distance, what is the force on each charge? We're returning to Coulomb's law. If I increase R by 3, I get a 1/9 over here. So it's going to be E is 1/9 F. Two balls plus Q plus 4Q are separated by distance 3R. Is it possible to place another charged ball Q0 on the line between two charges such that the force will be 0? Okay, the quick answer is yes, independent of the sign of Q0. That it can either be positive or negative. All right. I ask you another question too, and this is one that we asked in class, is where would it be? Would it be here? Would to get a 0 force, a net force of 0? Would you put that charge Q0 somewhere in this region, B? Or would you put it somewhere in this region, C? And the answer is that you would put it over here. Let me show you why. I'm going to erase this. We'll first assume that our charge is negative. Let's say that we have a negative Q charge. The force due to this charge is going to be in this direction. And then the force due to this charge is going to be in that direction. Notice that even though this charge is bigger, because I'm further away from it, that force is smaller than it would be if you were closer. Then, if I have a positive charge, over here, the force due to this charge would be in this direction, and then the force due to this charge would be in this direction. And because I'm further away from the 4Q charge, my force is less than it would be if I were closer, so that these two charges will be equal but opposite, equal in magnitude but opposite in direction. Okay, so the answer is C, and in this case, it has to be the left of the center in order to have that. You have to be closer to the smaller charge in this case. All right, proton and electron are held apart at a distance of 1 meter and then released. As they approach one another, what happens to the force between them? All right, well, F equals KQQ over R squared. As R gets smaller, F goes up. All right, by quite a bit, actually. Like if I plot F versus R, it's an inverse square relationship, and it looks like this. As you go far away, F gets really small, but as you get closer, F gets really big. So the answer is A. It gets bigger. It gets a lot bigger, actually. Proton and electron are held apart at a distance of 1 meter and then released. Which particle has a larger acceleration? Or well, they both feel the same force. We already know that from Newton's third law and the Coulomb's law. But the one that feels a larger acceleration is the lighter of the two, because F equals ma. They feel the same force, so this is held constant. But if m is small, the acceleration has to be bigger, and that's true for the electron. Proton and electron are held apart at a distance of 1 meter and then let go. Where would they meet? Well, because the electron is accelerating more quickly, you're going to meet closer to the proton side. Which arrow best represents the direction of the net force on charge plus Q to the other two charges? All right, well, this is similar to the one that we had before. I'm going to draw my force vectors. So due to this charge, my force vector is going to look like that. And then due to this charge, my force vector will be smaller, look like that. So let me redraw. I'm going to make this one bigger. So this, number 2, RB, we'll call it. You're sitting at a certain distance from a point charge. You measure an electric field. If the charge is doubled and your distance from the charge is also doubled, what is the electric field strength now? Well, E is equal to KQ over R squared. So what I'm doing is I'm doubling Q and I'm doubling R. So over here, that gives me a 4 in the denominator and a 2 there. So I get 1/2 of the original electric field strength. Between the red and the blue charge, which of them experiences the greater electric field due to the green charge? The answer is they both experience the same electric field. The electric field at this point is the same. I can calculate it, right? It's E is KQ over R squared. Right, now they're going to experience different forces due to that electric field, but they shall experience the same electric field. Between the red and the blue charge, which experiences the greater force? Well, the force is equal to Q times E. They both experience the same electric field, so the one with the bigger charge will experience the bigger force. So the +2 charge experiences the greater force because it just has a bigger value for Q. Uniform electric field, a 4 Coulomb charge is placed and it feels an electrical force of 12 newtons. If this charge is removed and a 6 Coulomb charge is placed, the point is said, what force will it feel? All right, we just had to sort of solve for this. So F is equal to QE. I have 12 newtons on a 4 Coulomb charge. So that tells me that my electric field is 3 newtons per Coulomb. And now I want to know the force on a 6 Coulomb charge. So that's 6 coulombs times 3 newtons per Coulomb, and that's equal to 18 newtons. So E is the right answer. What are the signs of the charges whose electric fields are shown? Well, electric fields come out of a positive charge and end in a negative charge. So that is B. Which of the charges has the greater magnitude? The one with a larger number of field lines. It has a magnitude that is twice the magnitude of the green charge. So my ratio of red to green would be 2 to 1.